Well, hello and welcome back. This is a supplemental lesson where I'm going to cover a few remaining topics in quantum mechanics, but I wanted to call it supplemental to sort of get it out of the main stream of development of this thing, although the entire geometric algebra portion of this is obviously a big diversion to the whole notion of QED prerequisites, but this is where I've brought us. I want to begin with an errata. So let us start with an errata from the lesson on amplitudes and eigenvectors. Okay, so I have two errata that actually undo each other, and I made two mistakes, and the two mistakes actually undid each other and gave me the correct answer. So I didn't notice the mistakes because I got the correct answer, which is sort of this annoying process. But again, a good viewer saw this problem right away because, and the reason he saw the problem is because I keep insisting when I'm dealing with things like this, right? This is supposed to be, remember what this is supposed to be. This is supposed to be I sigma 1 adjoint, which is supposed to be gamma 0, I sigma 1 reverse of both of them, gamma 0, right? So I'm still sort of leaning on just breaking it all out and calculating everything. I actually did that correctly, though. It's not like I did this wrong. So it does break out into this. It does give you this piece. It does give you this. And ultimately, that does give you minus gamma 3, 2. And then I did correctly calculate what I sigma 1 was in itself, and it is gamma 3, 2. So there's a sign difference between these two. But when I went and I substituted back I sigma 1 here, I need to account for that minus sign by including the minus sign right here. And as you can see in the original work, I didn't do that. So now I have this red minus sign to remind me that I screwed that up. So that red minus sign floats up there with the adjoint calculation. So this piece here has this new minus sign. So you would think that would screw everything up. But I also, when I substituted for psi, and I put in the substitution there, I had two minus signs. I had these two blue minus signs here, or black, I guess, here and here. But the psi is just a regular spinner, so it should follow this pattern that we did when we straight up calculated it out of here, right? I just replace delta, theta with delta and little psi with, what did I use? Eta, right? So it should have the exact same structure as phi should have the exact same structure as psi, which means a minus sign floating in front of the I sigma 2 piece. Well, it didn't, right? Well, no, the minus sign was floating in front of the I sigma 2, but I should have a plus sign floating in front of the I sigma 1. However, luckily for me, this minus sign up here is compensated exactly by the negative sign down there. And so this product was the only thing that was wrong. And but the two signs still work correctly, and I end up with this. I'm pretty sure that's all that happened there. So I end up with this real part. Okay, was there another errata? I think so. Hold on. And yes, this error flowed through my calculation of the amplitude. So fixing it here by adding that minus sign there and the minus sign here, or turning this into a plus sign, then working on the conjugation or multiplying phi by what would be in the Pauli system an imaginary number, but multiplying by the pseudoscalar in sigma 3, that sign just sort of floats around and propagates through. This should be a minus sign here. And then when I try to calculate this entire piece, I have to introduce a minus sign on the I sigma 1 part, and I have to change this plus sign to a minus sign on the I sigma 2 part. There's another little minus sign floating in there, and those two cancel each other, and then you multiply by that plus sign. So you end up with a plus sign here where there was a minus sign, and you end up with a minus sign in front of this term where there used to be a plus sign. And so what that ends up doing is that ends up flipping the two trigonometric expressions around, which reverses the phase, and sine is a odd function, so I pull that sign out because I want the phase to look like it should in the original. So that sign, this I triple three part, that sign is wrong. And now this one I should have been able to detect because I actually did the calculation in the Pauli system, right? And it is a plus sign here. And here with that minus sign, and we plug into this formula, we get that plus sign back. So I should have been able to pick up that one, but I missed it. Okay, so ironically, this doesn't actually change anything because when you take the magnitude of this to calculate your magnitudes and all of these things, um, uh, this minus sign ends up uh, squaring away, but that error floats right into there, and so we end up with the correct magnitude in the end. Okay, so that's the errata. Thank you very much for the viewer who pointed that out. And now on to the new topics. Oh, and this user pointed out something easy. You know, instead of always leaning on this, I just can't seem to resist the temptation to, where was it, to lean on these long calculations. Where did I do it? Hold on. You know, instead of leaning on these long breakdowns, uh, this user pointed out these obvious little facts that, if I was good at geometric algebra, this would be very intuitive, right? You would think in these terms, right? But I sigma k, right? That's the dual of sigma k. It's going to be a relative bivector, right? A relative bivector. Now, a relative bivector has two gamma zeros in it, and it has two gamma k's in it. So you know that if you have a gamma zero over here, it's going to anti-commute twice, which is basically commuting. So the gamma zero will always commute through a spatial bivector. So if there's a gamma zero sitting over here already, this guy will just immediately commute to there and it'll clear, right? So if you ever write I sigma k, if you have a gamma zero, that's just going to be I sigma k, right? It's not going to change. So the idea here is that this doesn't change. If you do a reversion of this, you're just going to get some reversion of that. It's still going to end up with the same essential thing. So gamma zero is going to flow through the reversion. So the point is that I sigma k adjoint, right, is nothing more than I sigma k reversion, which is sigma k reversion, I reversion, but I reversion is just I, and sigma k reversion is just minus sigma k, but I and sigma k commute, so you always end up with just minus I sigma k. So the point is the adjoint of I sigma k is just minus I sigma k. Think how much time I would have saved if I had known that, right? Or I guess I kind of knew it, but if I applied it, let's put it that way. Let's say I applied it. Then immediately here, calculating this thing, I say, oh, I just need I sigma 2 reversion. So I would just immediately change the sign uh, for the sigma 1 piece. I would have just immediately, where is it? I would have just immediately changed the sign for the sigma 1 piece from a plus to a minus, right? I would have done this. I guess I lost my sign change there. It should be a red sign change, right? That would have been a minus sign. And, oh, no. Wait. Sorry. I would have made the change. I left it in this weird form here, so it kind of keeps those signs. I just had to remember to change it down here. And I did for sigma 2. I got that sign change right. But I wouldn't have had to go through all this. I would have just looked at this and said, oh, just change that to a plus and change that to a minus, which is, of course, exactly what ultimately happened, right? So what I'm basically demonstrating is that I'm not really very facile with basic geometric algebra manipulations. However, in this lesson, we are going to talk about a couple other things that I kind of worked through to try to develop that facility so I wouldn't make these mistakes. And I just kind of got lucky that these mistakes compensated for each other in this calculation, but I got unlucky in that they did not compensate for each other in this calculation. Okay, so thanks again, and now let's go on to some new stuff. All right, so we've covered this basic material here, right? I've kind of shown how to take a Pauli spinner and produce a geometric algebra vector. Now notice there's other representations for Pauli spinners. This is, if you use the standard classic representation for Pauli spinners, then this is the formula. If you change it, then this formula is going to change a little bit. The ordering of these objects is going to change. This will always be the same, but you're going to have to shuffle these guys around. That's more of an issue when you're dealing with the Dirac version of everything, because we do I don't know of too many instances where we change the Pauli matrices around, but the Dirac matrices we change around all the time. In my experience, at least. We learned how to do these operator calculations using these various formulas here. We learned how to multiply by the complex scalar I and what that means, what that formula is in the geometric algebra. We learned how to calculate this amplitude, and we learned how to calculate the probability, I guess is what we would say. So, but there are a few other things that I think are interesting. I guess we also learned how to calculate the adjoint, right? I should also say that, psi adjoint, right, equals gamma 0, psi reverse gamma 0, right? So we learned all those things. So what do we want to talk about now?
So the next thing that Duran finds really important to discuss is the expectation value of an operator using the formalism of geometric algebra. And we have everything we need to study this. And what we're ultimately going to learn from this analysis is that we can treat spin in a slightly more holistic fashion using geometric algebra than you can in the Pauli formalism. So I kind of unpacked everything he said in his 2 or 3 paragraphs on the subject into this very long little essay. But hey, that's just how we roll here on this channel. So let us proceed. So the first thing we note is that we are able to calculate this expectation value, right? We just did it at great length. So the only distinction here is that this vector, which is the transformation of the vector psi by the operator sigma k, well, we just replace that. We replace sigma with this, right? So that's not a problem because we know how to write this kind of structure down in the geometric algebra. We simply use this formula, right? Whenever we operate on a spinner with an operator, we are using these. We multiply by the geometric algebra version of the vector on the left, the spinner in the middle, and on the right, sigma 3. And so I'm going to replace this with sigma k psi sigma 3 for the first half of the expectation value, and then in the second half I put it right there, right? And then of course in the second half we have to multiply by I sigma 3, take the 0 grade part and multiply again by I sigma 3. And likewise we take the 0 grade part of all of this stuff. So this is our formula to work with, and I'm just going to crunch it the way I imagine Duran crunching it based on his explanation. But this first part, he basically leaves alone until this step here where he does a cyclic permutation and moves sigma 3 to the left. And the reason is it's not something that would be obvious to do, but first of all, any cyclic permutation of the 0 grade part of things, right? If you have a geometric product and you're asking for the 0 grade part of it, you can take any cyclic permutation of the geometric product and you'll get the same 0 grade part. So you get free cyclic permutations. But the reason he wants to do this is because this guy here is what ends up playing a very important role in our understanding of spin, right? It basically, or something very similar to this object in red. And so he wants to collect these guys together. And this is sort of being motivated by how it ends up. So, but understand that it's a totally legal move to do a cyclic permutation in there. Then over here, we use our knowledge of the fact that I commutes with sigma 3. And so we move I over, and then the sigma 3s are together. They multiply up to 1 in the relative algebra. And so then we're left with this structure here. And furthermore, I know that I commutes with psi as well, and it commutes with all of the basis vectors. So I can continue to commute I over until I have this structure here. To convince yourself that I commutes with psi, I think I did some work on that. Where did I do some work on that? Yeah, I kind of actually worked it out the long way. Sometimes I simply can't resist, but you know, it's always something you're allowed to do if you want to work things out the long way. And, you know, I commutes with sigma I, commutes with itself. So sigma psi I is equal to I psi. And here's the analysis of that. So we're left with this guy right here. And then what Durand points out is he says, hey, the reverse of this, the geometric product inside these grade selection brackets, the grade 0 selection brackets, just remember there's always an implied 0 here when there is no number there. You think of it as 0. And now you do have this issue of, are we thinking of this in terms of the 4-dimensional space-time algebra or the 3-dimensional geometric algebra? And I don't think it matters, but because the grade 0 part in both cases will be the same. The problem, there is some ambiguity if you wanted, say, the grade 1 part. If I wrote a 1 there, then the question is, am I talking about the grade 1 part of the space-time algebra or the grade 1 part of the relative algebra? Because remember, the grade 1 part of the relative algebra is a grade 2 part in the space-time algebra. So the way Durand deals with that ambiguity is if he wants a grade 1 part, if he wants a grade 1 part of the relative algebra, he'll put a little v there for vector. So you've got these notational issues coming up. But it doesn't really matter. If you do this reversion, right, which is sometimes, I like to put the reversion over the whole thing, but typographically you usually see it written as sort of an exponential of the associated geometric product. But we just draw the reversion and we reverse we write the reversion of this structure and then we reverse each object, right? So we end up with this structure right here. And then we do each of these reversions. And we know that psi reverses to psi adjoint. And we know psi adjoint reverses to psi. Now we have to say, okay, sigma k, well, if we're doing the reversion in the relative algebra, it doesn't reverse, right? Because it's a vector in the relative algebra. But I in the relative algebra, right, I is sigma 1, sigma 2, sigma 3, which is minus sigma 2, sigma 1, sigma 3, which is plus sigma 2, sigma 3, sigma 1, which is minus sigma 3, sigma 2, sigma 1. So this was I, right? And this is I reverse. So I equals minus I reverse in the relative algebra, right? In the relative algebra. Now, if we were doing this in the space-time algebra, this would have been different. I actually equals I reverse in the space-time algebra, but sigma k equals minus sigma k reverse equals minus sigma k in the space-time algebra. So the origin of this minus 1 could come from either one. Regardless, the minus sign comes out and you end up with psi adjoint I sigma k psi, which is this here is this part is the same as this part, which means the reverse of this object is minus itself, right? And that's the point that we want to weigh here, that's the point we want to understand, is that this object is the reverse of itself, which lends us to thinking about, well, if it's the reverse of itself, if an object, I guess I should write this out, if a multivector M, if its reverse equals minus M, then it basically can't have a scalar part, right? Because the reverse of something with a scalar part won't be minus itself, because the scalar part doesn't change. So that means this thing, this grade zero selection on whatever that product is going to be zero. So we can ignore this entire piece of our expectation value. So our expectation value calculation is all living in this part right here. We can ignore all of this. So let's proceed with that. So I'm just going to shuffle this down here. So this goes away, and all we're left with is that. And I do another one of these cyclic permutations, right? Now I shift, I guess I'm shifting sigma 3. I want sigma k to be all the way on the left, right? So I shuttle sigma k over here. Actually, when I said earlier that this thing is the critical thing, that's incorrect. What I meant was, ultimately, this thing, this thing is going to be the critical thing that we're going to study. This is just some intermediate. This one here is just some intermediate piece. I mistook it. I was a little bit ahead of myself. This piece here is ultimately the thing that of interest to this subject. So we do some more shuffling until we have sigma k, our operator, on the left, and psi sigma 3, psi dagger on the right. What should have been a hint is this actually kind of looks like a rotation of sigma 3, right? If you treat these guys as rotors, the psi as rotors, right? Which you can, right? This structure here, the structure, A0 plus AI I sigma I, right? That this is a bivector, right? And so this structure here is going to have the structure of a rotor, right? So we look at this spinner as like a rotor acting on sigma 3. So that's ultimately that's a little foreshadowing of the way we want to interpret what spinners are in the geometric algebra. They're actually instructions to rotate things at some level. There's a few caveats, but we'll get there. So we end up with this structure right here. So now we break it down, as I was just saying, into a geometric. We use the associative rule, and we're going to associate this geometric product of four objects with just 3. And let's just take a look at that, right? There's a lot of ways of looking at this, some more tedious than others, but the point I want to make is just look at this. We're looking for the zero grade part of this total geometric product. So whatever this is, it's some multivector that can be blown up with a scalar part, a relative vector part, a relative bivector part, and a relative trivector part, or a pseudoscalar part. So if you use linearity of the geometric product and you multiply through by sigma k, well, this piece here, sigma kb, that's a vector part. So that doesn't contribute to the zero grade piece. This piece here, sigma k against the vector part, well, for all of the sigma i's that are not equal to, for the sigma I that is equal to sigma k, that will actually be scalar. But the rest of the sigma i's will be bivectors. Here, if sigma I or j equals sigma k, you'll end up with a vector. If sigma I and sigma j are the same, right, then this will reduce to a scalar piece, which when multiplied by a vector is still a vector. And if And then this last part here is a trivector, so multiplied by sigma k will be a bivector. So the only piece that survives really is this part of the product, Ci sigma k sigma I, which is Ci sigma k dot sigma I, because the wedge product part of this geometric product of two vectors. Now remember, we're treating these as relative vectors. So sigma I sigma k is going to be sigma I dot sigma k plus sigma I wedge sigma k, right? So if sigma I and sigma k are the same, this part goes to 0, and then you get sigma I dot sigma I, which is going to be 1, right? So that's basically, ultimately this ends up being a delta function, right? This here is a delta function sigma ki. So you end up with just your scalar piece. So the point is that the grade 0 part of this product can ultimately be thought of as sigma k dotted with the vector part of this product, right? This product, we've got to find the vector part, and the way we write that down is we would write a little v here, right? And so now we have a new formula, sigma k dotted into a vector, which is important because now we're saying that the expectation value, which is a real number, right, is given as the sigma k component of some vector. But now we can actually go a step further, because if we study this independently, just the stuff in the middle, if we study this, what we see is that this must be a vector, right? So let's see if we can understand why must that be a vector? Well, to start with, if we take this object here and we blow it up, right? Let's just do it the hard way. Blow it straight up and multiply out all of these parts, right? Multiplying on the left by sigma 3. So we get this vector, and this is a bivector times a pseudoscalar, so this is a vector piece as well. And then you have a vector piece and a scalar piece, and then if you blow all that up, you get this vector piece on the left, and then you get the two inner parts actually cancel, right? So the stuff in the middle cancels, and then you end up over here with what is sigma I, sigma 3, sigma j. And if I and j are not sigma 3, you end up with a pseudoscalar, right? If this is sigma 1 and sigma 2, you end up with a pseudoscalar. If I and j are the same, you end up with a vector. So this is a vector or a pseudoscalar, and this is a vector. And the point is the even part is gone, right? This part is the even part, and there is no scalar part. Or embedded in here in principle, there's scalar and bivector pieces, right? Depending on j and I, right? Well, in principle, you can get a lot of different things, I guess. Well, first of all, remember, they cancel. So whatever you get here, whatever you get out of this term doesn't matter. These guys cancel. I commutes, and you have 3j, and you have I3, right? So this is going to completely cancel. But just as an academic exercise, if I was 3, this would go away, and you'd end up with a pseudoscalar part. If I is 1 or 2, then it becomes a vector part. So this, even if it didn't cancel, it's pseudoscalar or vector. So anyway, the point is this guy here is a pseudoscalar or a vector, and the point that is Durand notices that means it is Pauli odd, because remember, it's a vector part or a pseudoscalar. Those are odd, right? You have the scalar part and you have the bivector part, right? Those pieces are missing, so these are the even pieces. The odd pieces are there. So this is Pauli odd. But he also notes, Durand also notes, but look at this thing here. He also notes that this guy is Hermitian symmetric, which means it equals its own Hermitian conjugate. And if you were to work this out the long way, right, by taking the gamma zeros on both sides, reversing everything and reversing everything, you would quickly see that that you would get gamma 0. This becomes psi. The reversion of sigma 3 in the space-time algebra gives a -1 sigma 3. And this becomes psi bar, and this becomes gamma 0. And then you'll notice you can do the calculation yourself, but gamma 0 commutes with the psi's, but it anti-commutes with the sigma 3, so that minus sign goes away. So this ends up being, and then it clears itself on the far left. So you get this thing all the way over here, and then that clears. The -1 gets to be a +1, and of course you end up with psi sigma 3 psi adjoint, which is equal to this self. So it's Hermitian symmetric but Pauli-odd. So the only way you can be Hermitian symmetric if you're Pauli-odd is if you're a vector, right? The pseudoscalar, right, is going to, the pseudoscalar part is going to be Hermitian antisymmetric. So the point is by writing, I want the vector piece of that. I erased it, sorry, but I want the vector piece of this. But it turns out, because it's Pauli-odd and Hermitian symmetric, this thing only is a vector, right? So it must be a vector. So I can actually write this in a more simplified way by just writing sigma k dot psi sigma 3 psi adjoint, right? Because I know this guy's a vector, so I don't need these braces anymore. Okay, so let's take this for a test drive. This is our current state of affairs. We now know that to calculate this expectation value, we are going to take the sigma k component of this relative vector, right? That's what this formula says. Find the k component of this relative vector using the geometric algebra process. Now, I think Durand makes the statement that, oh, look, we have everything that we need is embedded in this spin vector. All three components are all we need. But here in this Pauli formalism, we have to deal with each component separately, right? There's no way of binding them together into a single object like you have here. And I take note of that, I suppose. I do know that if you actually want those numbers, you have to extract them one at a time. But one of the points that he's trying to make is that this is a new way of interpreting spin, right? Because here's a vector. How can you know the three components of a spin vector when we know that they, without that you can't measure the three of them simultaneously, right? There is that prohibition in quantum mechanics. Now, this allows you to do the calculation pretty straightforward, but ultimately, all of that is taken care of by the non-commutivity of the basis vectors. So everything is based in geometry. You're not looking at the non-commutivity of these mysterious operators. You're just looking at, hey, this is how basis operators work in the geometric algebra. I'm not sure if I have fully absorbed the significance of that, but take note that this is supposed to be a very, very important step. I'll study it a little more and maybe discuss it in another video later. But let's look at it for three different circumstances here. First, let's take psi to just be your standard up state, which is represented in the geometric algebra by the scalar 1. So this is the height of easy. If I wanted to calculate, say, the expectation value of the sigma 2 operator, as I would normally think of it in Pauli terms, I would take the dot product of this with 1 sigma 3 1, right, which is going to be sigma 2 dotted into sigma 3, which is going to be 0. And that does make sense, right? Because the expectation value of the projection in sigma 2 of something that's up in sigma 3 is going to be sometimes minus sigma 2, sometimes plus 1, sometimes minus 1. So that actually makes sense. I guess I should just prove it in the Pauli system, right? This is the calculation using the Pauli system, and you end up with 0. And obviously, if I had changed this to sigma 3, then this would be sigma 3 dot sigma 3, and it would be 1, which is just a repeat of our eigenvalue expression. The expectation value of the upstate, when you measure the upstate, is going to be 1, right? That's the whole point. That's actually as close to realism as quantum mechanics comes, when the probability of something actually equals 1. Now, if we did this calculation for the downstate, we said, okay, what is the expectation value of sigma 2 in our downstate? Well, I need minus I sigma 2 for our downstate in the geometric algebra representation, sigma 3, and then I need the adjoint, which is I sigma 2. Right, and I take this dot product, so let me flush out the right-hand side, which is, this is going to be sigma 2 dot, the i's will come together, commute through the sigma 2 and sigma 3. The minus sign will therefore go away with I squared, but you'll reintroduce a minus sign by flipping the sigma 2's together. Those two will come together to be 1, and you'll end up with sigma 2 dot sigma 3, which, again, is going to be 0, which is, of course, the same. You wouldn't expect it to be any different. I will say this is actually almost a little bit quicker. This now, I'm actually beginning, this calculation that we just did would be a little bit easier than doing it the matrix algebra method. But likewise, if I turn this into a sigma 3, though I'd have a sigma 3 here, and sigma 3 dot sigma 3 is 1, and therefore the expectation value, where's the minus 1? There should be a minus 1, right? Yeah, okay, I have to be more careful in this, right? The i's come together and commute, right? So you end up with minus I squared, sigma 2, sigma 3, sigma 2. So this I squared cancels with that minus 1, leaving us with sigma 2, sigma 3, sigma 2. Then you commute these two and you get minus sigma 2 squared sigma 3, which is minus sigma 3. Right? So this guy is going to end up being sigma 2 dot minus sigma 3, which is still 0, right? But if you replace this with sigma 3, you end up with a sigma 3 here, and then that ends up being minus 1, which is the correct expectation value. Okay, so there's how you calculate those two expectation values. So now let's look at something a little more fun. Let's look at, this is the eigenvector for sigma 2, right? So this calculation shouldn't be, now that we understand what we're doing, we think, to calculate psi sigma 3 psi adjoint, we would get, let's see, what do we get? We get we get 1/2 because the two square roots of 2 come together. We get 1 plus I sigma 1, sigma 3, 1 minus I sigma. We've learned that the adjoint of these spinors is just the opposite of the bivector part. And then we proceed with that product. So I'm running this calculation, just multiply everything out, multiply sigma 3 on the left, then expand expand these two terms together. These guys combine with a minus sign correcting, so you end up with a factor of 2 there. This ends up being sigma 3 minus sigma 3, and that's a sigma 3, so those two cancel, so you end up with this. The 1/2 cancels the 2, you end up with I sigma 1 sigma 3, and that is sigma 2. And so this guy here equals sigma 2, so the expectation value, say, so S, our spin vector, equals sigma 2. And so, okay, so the expectation of value of sigma 3 on S equals sigma 3 dot sigma 2, which equals 0. The expectation value of sigma 2 on S is sigma 2 dot sigma 2, which equals 1. So this is basically representing the up state of the sigma 2 operator, which is exactly what we expect. So now I'm going to go back to our summary page, and we're going to add expectation value of psi sigma k psi equals sigma k dot psi sigma 3 psi adjoint. Nice. So now we have all these formulas to work quantum mechanical problems with. Eventually we'll have enough of this stuff that we could take your standard quantum mechanics, elementary quantum mechanics problem and solve it using geometric algebra. So the next step would normally be, the next step we should take in our supplemental review of some of this information is understanding this as a rotation, right? Understanding the spinner as an instruction to rotate sigma 3. And that's actually pretty interesting because now we're actually seeing spinners as something that's literally spinning something. But it's not being treated as a state. It's being treated as an operator to rotate the sigma 3 basis vector. And this to me is pretty interesting. I think seeing spinners as instructions is truly a new way of seeing it. I mean, if you're a guy like me who's gone through quantum mechanics his whole life thinking of spinners as states, as part of state vectors, as members of a vector space of states, and now we're thinking them as instructions to control the position of a little coordinate system. That's pretty interesting. I'm not fully understanding it all right now, so I'm not going to do it in this lesson, but the next supplemental lesson will explore that idea. So I'll see you next time.